Imagine a battery that doesn't just power your home, but actually cleans the ocean while it charges. For decades, we've kept water as far away from batteries as possible to avoid catastrophic failures. But a team at the University of Surrey has flipped that logic on its head. They've developed a system where water isn't the enemy, it's the secret ingredient that makes the whole thing work. This is the NVOH battery, a breakthrough that uses a unique wet chemistry to solve two of humanity's biggest problems at once: energy storage and freshwater scarcity. To understand why this is so radical, we have to look at the limitations of the lithium-ion batteries currently in your phone and car. They rely on organic electrolytes that are highly flammable. Water-based or aqueous batteries have always been the dream because they're non-flammable and cheap. But until now, they couldn't hold enough energy to be practical for the grid. The Surrey team found a way to bridge that gap using a material called sodium vanadium oxide hydrate. It's a mouthful, but its physical structure is a masterpiece of engineering. In February 2026, the researchers revealed that this specific material can store energy in a way that looks more like a sponge than a traditional electrode. It actually likes being wet. This isn't just about storing electricity. It's about the mechanical movement of ions through a liquid medium. The wet nature of the system is what allows it to perform its secondary trick. By embracing water instead of fighting it, they've opened the door to a battery that is safer, cheaper, and potentially more useful than anything we've seen before. The secret lies in the hydrate part of NVOH. Most battery materials are dry, but this one has water molecules baked into its very crystal structure from the start. Think of it like a building where the scaffolding is made of water. These internal water molecules act as spacers, keeping the layers of the material open so ions can fly through. Without these water spacers, the material would collapse under the stress of charging. But with them, the NVOH remains stable, allowing for a massive boost in charge capacity. This leads us to a fascinating question. If the battery is already full of water, what happens when you put it in the ocean? That's where the mechanical breakthrough truly begins. The Surrey team realized that the same forces that pull sodium ions into the battery could be used to pull salt out of the water. It's a mechanical process hidden inside a chemical one. It's a complete shift in how we think about hardware. Next, we're going to look at the exact nanostructure that makes this salt stripping possible. At the heart of the NVOH battery is a nanostructure that looks like a series of microscopic tunnels. These tunnels are precisely sized to let sodium ions pass, but they do something even more clever with water. The vanadium oxide layers are held apart by those structural water molecules we mentioned. This creates a pillared structure, much like the pillars holding up a massive highway overpass. This architecture is incredibly robust. It allows the battery to expand and contract during charging without the material cracking, which is a common failure point in other chemistries. But here's the genius part. The water molecules trapped in the lattice don't just sit there. They create a lubricated pathway that reduces the friction for incoming ions. Because the ions move so easily, the battery can charge and discharge much faster than traditional aqueous batteries. It's the difference between walking through mud and skating on ice. This mechanical lubrication is what allows the NVOH battery to achieve its high charge capacity, reaching levels that were previously thought impossible for a water-based system. Now, let's talk about the desalination magic. When you plug this battery into charge, it creates an electric field that attracts sodium ions from the surrounding seawater. As the sodium ions are pulled into the NVOH lattice for storage, they leave behind the rest of the salt, specifically the chloride ions. But the system is designed to trap those too. By the time the battery is fully charged, the water surrounding the electrodes has been stripped of its salt. You've effectively filtered the water just by storing energy. This process is called electrochemical desalination. In a standard desalination plant, you have to force water through tiny membranes at massive pressures, which uses a ton of energy. But the NVOH system uses the energy that was already going into the battery anyway. It's like getting a free glass of water every time you charge your phone. The efficiency is staggering. Because the salt removal is a byproduct of the charge cycle, the energy cost of the fresh water is virtually zero. The mechanical process of moving these ions in and out of the lattice is what makes the system wet. The water isn't just a solvent, it's a structural and functional partner. This coordination is what allows the battery to maintain its structure over hundreds of cycles, even while filtering harsh, corrosive seawater. But as with all engineering breakthroughs, there's a catch. And the catch for the NVOH battery is one that engineers are still fighting to solve. Every engineering decision is a trade-off. For the NVOH battery, the trade-off is its lifespan. While a lithium-ion battery can last for thousands of cycles, the current NVOH architecture hits a wall at about 400. 400 cycles might sound like a lot, but for a car you drive every day, it would only last about a year. This is why you won't see an NVOH battery in your Tesla anytime soon. However, the world of energy storage is much bigger than just cars, and for certain applications, 400 cycles isn't a deal breaker, it's a starting point. The reason for this 400 cycle limit is the gradual swelling of the NVOH lattice. Even with the water scaffolding, the repeated movement of salt ions eventually causes the structure to fatigue. Think of it like a sponge that's been squeezed and soaked 400 times. Eventually, it doesn't spring back quite the same way. This is the mechanical reality of wet chemistry. But engineers at Surrey are already working on self-healing versions of the lattice that could push this limit to 1,000 cycles or more. Even with the 400 cycle limit, the NVOH battery has a massive advantage over lithium: cost and safety. Lithium is expensive and difficult to mine, whereas sodium and vanadium are abundant. And because the electrolyte is just water, there is zero risk of the battery catching fire. You could literally hit it with a hammer or pierce it, and it would just leak salty water. For stationary grid storage, the giant batteries that keep cities running when the sun goes down, safety and cost are often more important than having thousands of cycles. The implications of this are huge for coastal cities. Imagine a single facility that stores solar energy during the day and provides fresh drinking water to the population at the same time. This isn't just a battery, it's a new type of infrastructure. It turns the ocean, the very thing that usually destroys electronics, into the lifeblood of the system. By solving the mechanical challenges of the NVOA lattice, we're not just making better gadgets, we're rethinking how we survive on a changing planet. The next time you look at the ocean, don't just see a vast expanse of salt water. See a reservoir of energy and life waiting to be unlocked by a little bit of clever engineering. The University of Surrey's wet battery is a reminder that sometimes the best way to solve a problem is to embrace the very thing you were afraid of. Because in the world of engineering, the most elegant solutions are often the ones that work with nature rather than against it. And that is how we build the future.